Hello, everyone, and welcome. Thank you for being here today. My name is Arielle Raphael, and today I'm excited to present our project, RadioMesh, Building a Drone Communication Through Mesh Networking. I'm presenting alongside my teammates James, Kirk, and Alex Zurita. Our project is all about creating a way for drones to communicate without needing internet or a central control system. This is something that is crucial for drone networks in challenging environments. So today I will walk through how we're testing and building the communication system, starting with radio-based simulations. So let's dive into this. Oh, sorry. Okay. Picture this. Drones are used for things like search and rescue, wildfire monitoring, delivering supplies in disaster zones. Now imagine these drones having to operate where there's no cell service, no Wi-Fi, no GPS. How do they communicate with each other or with a central command? That's the challenge we're tackling. Our solution is a radio-based simulation that lets us test how drones from mesh networks. This is networks that can stay connected even when there is no traditional communication infrastructure. Right now, we're using radios to test message passaging, and network resilience. This will eventually translate to real drones, allowing to coordinate without relying on a centralized system. So here's the problem we're trying to solve. Most of today's communication system relies on fixed, centralized infrastructures like cell towers, Wi-Fi routers, and like satellite links. But in situations where drones are most needed, like in disaster zone, like wildlife areas, um, isolated areas, or places with conflict, the infrastructure is often damaged or is simply not there. Drones can easily lose connection when they fly out of range of ground stations or when they go behind obstacles like mountains or buildings. Without a way of communicating, they can't share vital sensor data, they can't coordinate with other drones, and they can't respond to mission updates or changes. So our goal is to create a way for drones to stay connected without needing infrastructure. And we're doing this by building a decentralized, self-healing communication network, all starting with radios. To build this network, we were inspired by how cellular networks work. In cellular systems, a radio network subsystem, also known as RNS, is responsible for managing how mobile devices connect to towers and maintain their connection as they move around. In our case, we adapted this concept for drones, but instead of connecting to fixed towers, each drone acts as its own communication hub. What this means, it means that each drone can automatically discover other drones nearby and keep communication going as they move around, whether they're flying in like a swarm or they're navigating through disaster zones. We're currently testing the behavior using radios by eventually it will be enabled to drones so they can coordinate without relying on human control systems. So how does this work? I'll break it down. Our solution is a scalable, self-healing mesh network. The idea is simple. Each node, whether it's a radio or in the future an actual drone, acts as both a transmitter and a receiver. If one node goes down for any reason, like battery loss or damage, the network automatically reroutes and keeps the communication flowing. As drones move in and out of range, the mesh network adapts and grows in real time. For example, let's say a search and rescue drone enters a collapsed building. Even if it loses direct contact with the command center, other drones nearby can relay this message through the mesh. By using radios for these tests, we're able to simulate how this will work in the air, where drones will need to rely on each other to stay connected. Our system is made up of three components: nodes. This is radios, or in the future, drones that can send and receive messages. We have communication links. These are wireless connections that form between devices, creating the network. And then we have mesh gateways. These are optional nodes that can connect to the external network if needed, but they aren't essential for internal mesh function. The key features of the mesh network are self-healing. If a drone goes down, other drones automatically will find a new path to keep the network running. And then we have scalability. This network can grow from a handful of drones to hundreds without needing central control. We are currently testing these features with radios, but these are the same principles that will apply when we deploy like actual drones. Now let's talk about how messages actually move through the mesh. So we have a step-by-step message flow for tracking a message from origin to destination. So we're gonna use this based off of drones. So if it says node, I'm gonna use the word drone. So imagine node A. So it would be imagine node drone A wants to send a message to drone D instead of node A to node D. It would be drone A to drone D. This is how it would work. So drone A will first send that message to drone B, and then that message will be forwarded to drone C, and then that message will be forwarded to drone D, which drone D will finally receive that message. It's a very simple process. This process is called multi-hop routing. This allows drones to stay connected even if they're not in direct range from each other. This is especially important in real-world scenarios like drones flying through mountains, urban areas, or dense forests where direct line of sight can be blocked by obstacles. Let's look at the technical subsystems that make it all work. We have subsystem 1, mesh network initialization. Mesh initialization is the key, or is a key. It allows radios and future drones to automatically discover and connect to nearby nodes where there's power. Uh, there's no need for manual configuration or a central list. The system builds its own communication map, which makes it perfect for deploying drones in unknown or rapidly changing environments. We have subsystem 2. This is message routing logic. Our routing logic is designed to evaluate the best available paths for data. If drones fly behind an obstacle like a hill, the system will instantly reroute the message through other drones to maintain smooth communication. And then we have subsystem 3. This is data handling module. This is the data handling module. The data handling module system ensures that the network can handle different types of data, whether it's simple text updates or like thermal images or live video feeds. The system ensures that the data is compressed and transmitted in a way that it's reliable and efficient. We have subsystem 4. This is user interface. Our user interface lets operators monitor the network status in real time. They can see which drones are connected, send messages, and troubleshoot any issues that might arise during a mission. And then lastly, we have subsystem 5. This is RNS integration, also known as resilient networking system integration, ensuring that mesh networks remain stable even when drones are lost or damaged. The network will automatically recognize itself to keep the mission going without human intervention. And then we have a level design. This is just a reiteration of what was said earlier, but we have our mesh clients. which is the drones and radios that send and receive data. We have our mesh routers. These are the drones that forward messages to other drones in the network. And then we have mesh gateway. These are optional drones that connect to external networks, if necessary. We have their interaction. This just means mesh clients communicate with each other through mesh routers, which dynamically routes messages across the network. The mesh gateway provides optional connectivity to external networks, enhancing the system's versatility. Each drone plays a key role in keeping both the mission going and the network stable. Lastly, we just want to show where we are like at now. This is our project progression. We have built a resilient multi-node mesh using ground-based radios. We have successfully implemented features like node discovery, dynamic routing, and failover handling. We transmitted compressed images and videos through the network and tested how it heals itself after the node fails. In the future, we want to implement this more with the drones, but we are not there yet. We also have a demo where we will be showing our RadioMesh simulation, but this will be via Zoom class session, April 28th via Zoom during our class session. Um, and that is our project progression. Lastly, our question and feedback. To wrap up, Radio Mesh is more than just a radio project or just another radio project. It's the foundation for drone fleets that can operate without relying on traditional ground-based communications. So by simulating this with radios today, we're preparing for real-world drone deployment that will be able to explore, save lives, and carry out complex missions in the environment. So without the need of centralized systems, or if they're not available. So I'd like to thank everyone for your time today, and me or any of my other group members would love to answer any questions you have or any points of confusion, and we would love to see any points where we can improve. And thank you.